Hey guys, welcome once more to our YouTube channel. If you're looping in for the very first time, our YouTube channel is a consequence of our deep passion for the world of science and our willingness to reach out and share some of this love to people out there as we help them in preparing for their end of year exams and also national entrance examinations. If you find value in this video, please consider liking, subscribing, and sharing the content, hitting that like button, and of course commenting down in the comment section below. This all helps the YouTube algorithm to push our content forward. Thank you so much. Let's dive in. Alright guys, so today we are going to be continuing with the Therese Premock, the part 2 of it. So if you've not yet checked out the part 1 of the video, you can find the part 1 at the end of this video, or down in the video description you would find a link to the part 1. So let's dive in. Alright, so you can just pause the video and then read the question, and I actually attempt it. Alright, so you notice here that the question is basically talking about Newton's second law. So Newton's second law basically states that the rate of change, or the time rate of change of momentum, is proportional to the force applied and takes place in the direction of the force. Okay, and so we can mathematically write it out like that. And so we notice that V and U here, we can interchange them because, well, the force exerted on the seatbelt is equal and opposite to the force that the seatbelt exerts on the passenger. Okay, so your V technically can be U and your U technically can be V. So technically here we are using U as V, so U is 0. Okay, so we have mv over t. So we put in our values, and so our F is 7,500 newtons, which gives us the answer to be D. A conductor wire having 10 to the power 29 free electrons per meter cube carries a current of 20 amperes. If the cross section of the wire is 1 millimeter squared, then the drift velocity of electron will be. Okay, so we first have a diagrammatic representation of a wire here, and so there's a charge E here moving from one end to the other. So if the charge takes time t to move from one end to another, which the charge would have covered the distance L, then the drift velocity, of course, is distance over time taken, which is L over t, right? But you of course realize that the charge that has actually flown in this conductor is actually the number of electrons multiplied by the electronic charge, which is again equal to the current multiplied by the time taken for the current to flow. And so we can express time here in terms of number of electrons multiplied by the charge divided by the current. Okay, and so we can come back to this expression of drift velocity and replace, of course, our time here with this quantity. And so if you simplify, you get this. And so, but our volume of this wire is actually the cross-sectional area here multiplied by the length of the wire. And so the length is actually volume over cross-sectional area. And so you realize that our drift velocity, then we can replace further this L with the volume over cross-sectional area. All right, and so you realize that if we write IV over NEA here, now remember that this N here is actually just the number of electrons that are present in this conductor, right? Not the electron density. So electron density will be the number of electrons divided by the volume of the conductor. All right, and so you realize that the volume is actually here. So of course, basic in algebra entails that we can actually send this volume down, right? So we actually have N over V, right? And so you realize that N over V gives us the charge density, which is now capital N. Okay, so you realize that, all right, so that's basically the tweak I've done there. And so we can make now the drift velocity here the subject, and so it's actually I over NEA. And so we can substitute our information here. Our current is 20 amperes, our N, the charge density, is 10 to the power 29. All right, remember that it's per meter cube, so that's the charge density. Then the electronic charge is actually 1.6 times 10 to the negative 19, and our cross-sectional area is 1 millimeter squared, which in meters squared is 10 to the negative 6. And so you simplify that, our drift velocity is that, and the answer is C. Guys, may I just add that the previous question I just did, right, deriving that formula of drift velocity in terms of the current, the charge density, the electronic charge, and the cross-sectional area of the conductor, well, it's actually a past question, and it also came in Therese Premock last year. So watch out for that kind of question. All right, so the next one says a force of 5,000 newtons is applied outwardly to each end of a 5 meter long rod with a radius of 34 centimeters in Young's modulus of that. The elongation of the rod is, okay, elongation actually is a synonym for extension. All right, so of course we are going to write the Young's modulus expression, which is stress over strain, and then we are going to further simplify. Stress is force per unit area and strain is extension per unit length, and so our Young's modulus is FL over AE, right? I mean with algebra. So our E is basically, we make E the subject, and so we substitute the force, the length, the cross-sectional area, and the extension and the Young's modulus, and so you get that E is 0.55 millimeters, and so our answer is A. The magnitude of the acceleration of a satellite in orbit around the Earth is proportional to, okay guys, so I actually think that this problem has a little bit of a problem because, well, there are three correct answers here, right? And so the question should have read, the magnitude of the acceleration of a satellite in orbit around the Earth is proportional to all except, right? So that you get the one exception. But let's just discuss the problem and pick out the three possible answers I'm talking about. So of course, in orbit, what provides the centripetal force that keeps the satellite in orbit is actually the mutual gravitational attractive force the Earth exerts on it, right? Or it shares with the Earth. And so we have Fc equals to Fg, where Fc is of course the centripetal force and Fg is the mutual gravitational attractive force that the Earth and the satellite they share. And so the centripetal force is the mass of the satellite multiplied by the centripetal acceleration, which is equals to gmm over r squared, which is an expression of Newton's law of universal gravitation, right? Any two masses in the universe attract each other with a force that is proportional to the product of their masses and inversely proportional to the square of the mean distance between them. And so we can get the centripetal acceleration as gm over r squared, where this capital M is of course the mass of the generating field. All right, and so you realize that that is the mass of the Earth, right? And so the mass of the Earth, B, is one of the answers. Now if we go on and then we say, all right, but centripetal acceleration according to circular motion is always omega squared r, right? Where r is of course the orbital radius of the body executing circular motion, and so you realize that the centripetal acceleration is also proportional to r, right? Which is the distance between the satellite and the Earth. All right, the mean distance between the satellite and the Earth. So we can go on and then we say, but centripetal acceleration, because of course v is omega r, right? And so we can make omega the omega the subject, and then you realize that we actually have v over r. So a square that you are going to have v squared over r, right? And so centripetal acceleration is also proportional to what? The reciprocal of the distance between the satellite and the Earth. And so B, C, and D are all true, right? And so you realize that the only answer that is not true is of course A. So the question should have read all except, which in that case would have been A, the answer, right? Perfect, let's go on. For a negative point charge, the electric field vector, okay, so I'm just going to draw a diagram here between a positive and negative charge. This is actually a passage, this is a question. Notice that the field lines leave the positive charge and they are all entering the negative charge, right? Because field lines are actually taken as the direction of the force that this particular charge would exert on a unit positive charge placed at this point in the field, right? So this positive charge will be propelling, this negative charge will be attracting, and that's why they are entering. All right, and so the answer here is B, points radially in towards the charge for a negative charge, but for a positive charge they'll point radially outwards from the charge. Perfect. As a 10-kilogram mass on the end of a spring passes through its equilibrium position, the kinetic energy of the mass is 20 joules. The speed of the mass is, all right, this is very easy, right? Because they've given you kinetic energy around that equilibrium position and they're asking for the speed around that same equilibrium position. So I mean, like, there's really no work here. K equals to half mv squared, because at that equilibrium position the speed is maximum, the kinetic energy is also maximum. So there's, yeah, so at equal, Ke and V are both maximum, and so you have Ke to be equal to half mv squared, and so you realize that, well, you can make V the subject, and so when you get that, your V is 2 meters per second, and so our answer is A. A bullet is fired with a muzzle velocity of 1000 meters per second from a rifle clamped to a window 4.9 meters above the ground level. Neglecting air resistance, the horizontal distance from the rifle to which the bullet will strike the ground is, okay, so yeah, just notice that this picture is demonstrating how a bullet leaves the gun in the first place. So you notice that it's a horizontal velocity, right? It has no vertical initial velocity, okay? And so I'm going to diagrammatically represent it like this. Now, one key thing about projectile motion is that you have to understand that the motion is in two planes. Okay, so there's motion in the x plane and there's motion in the y plane. This single concept is what guarantees your full understanding of projectile problems, really. And so the horizontal plane, you actually realize that we can calculate the horizontal displacement as, of course, the velocity times time, because, well, this actually comes from the equation of motion that says distance is equals to ut plus half at squared. But in the horizontal direction, the acceleration is 0, right? Because the only acceleration for a projectile particle is actually the acceleration due to gravity, and acceleration due to gravity only acts in the vertical direction. So in the horizontal plane, a 0. Okay, so yeah, displacement in that direction is basically just u times t. And now in the vertical plane, your displacement, of course, takes the full equation of motion that describes displacement. And so you notice that we can get our time here to basically be 2y over g. All right, and so you notice that our t would be 1 second. Are we there? Because our uy is 0, that's what makes this equation like this. All right, so if our uy is 0, you notice that we can make t the subject here, so you get this. And so you substitute y, which is 4.9, and then you put g, which is 9.8, and then you get your answer as 1 second. Now our x is now going to, we just take this back and we substitute in here. Our ux is the speed of the bullet, and so you can multiply that with our time, which is just 1 second. So basically you have 1000 meters, and so our answer is C. The coefficient of thermal conductivity of copper is 9 times that of steel. In the composite cylindrical bar shown in the figure 3 below, what will be the temperature at the junction of copper and steel? Okay, so we are going to assume that, of course, this system is at steady state, and so our dq dt, which is the rate of heat transfer through the copper, will be equal to the rate of heat transfer through the steel. And so we can write out the expression for the heat transfer through the copper, the time rate of transfer of heat through the copper, which is basically the thermal conductivity of copper multiplied by cross-sectional area of copper multiplied by the change in temperature across the entire length of the copper bar divided by the length of the copper, okay, which will be equal to, of course, the thermal conductivity of steel to cross-sectional area of steel, change in temperature of steel, which is theta, because the temperature at this junction is theta, right? So you notice that I'm taking theta minus 0, right, as the temperature difference across the steel, divided by the length of the steel. So since we're looking for theta, temperature at the junction, we can just take those terms to one side, and so you'll notice that Kc over Ks here, thermal conductivity of copper is 9 times that of steel, so we actually have this Kc over Ks is basically 9, but the length of copper is actually 3 times the length of steel, because you have 18 and 6 here, so you actually have 9 over 3, which gives us 3 here. And so we make theta the subject. That's now mathematics, and our theta is 75 degrees, and so the answer is D. An iron ball at 65 degrees Celsius is dropped into a bucket of water at 65 degrees Celsius. Which of the following is correct? Well, you realize that we're getting two bodies at the same temperature, and we're putting them in contact, and so you realize that, well, they're at the same temperature, they are said to be in thermal equilibrium, because thermal equilibrium actually depends on the temperature difference between the two bodies. If the temperature difference between the two bodies is 0, then those two bodies are said to be in thermal equilibrium. All right, and so yes, these two bodies are at thermal equilibrium, but what happens when two bodies are at thermal equilibrium? That's the problem. What happens is that, well, the net heat flow between those two bodies is 0. I said net heat flow. It means that there's still heat flow, heat exchange between those two bodies, but the rate at which heat flows from body A to body B is the same as the rate at which heat flows from body B to body A. All right, and there's an interesting consequence to thermal energy right here, because, well, it's possible for two bodies to be at thermal equilibrium even though they have different heat content, because you realize that heat content depends on the mass and heat capacity of a body, while thermal equilibrium depends solely on the temperature difference between those two bodies, or the thermal potential between those two bodies. All right, and so the question came in the STEM. The STEM is the national exam we give to high school students to promote scientific thinking and critical thinking amongst them, of course with cash prizes as rewards. There was a question there that said, between a cup of hot water and the ocean, which one has a higher thermal energy? Though the cup of hot water has a higher temperature, the ocean has a higher thermal energy. Right? Because thermal energy is the sum total of the PE and KE of every molecule that makes up that system. And so the ocean is more massive, right? And so you realize that if you sum up the PE and PE of all the molecules that make water molecules that make up the ocean, it becomes higher than the water molecules, the PE and KE of the water molecules that make up the cup of water, right? And yeah, so you realize that thermal equilibrium depends on temperature difference, but heat content does not. All right, So again, it's possible for two bodies to be at thermal equilibrium even though they have different heat contents. Okay, and so you just have those summarized down here, and so our answer is actually the heat flowing from an heat from iron ball to water is equal to the heat flowing from water to iron ball. Perfect. When an object of weight W is suspended from the center of a massless string, as shown in the figure 4 below, the tension C at any point the string is. Okay, this is an easy peasy question. So you just come over here and then you resolve this tension. The vertical component is going to be T cos theta. Vertical component of this guy is going to be T cos theta. So we get those two guys, we sum them up, it gives us W. And so basically we make T the subject. And so our answer is B. If water is warmed from 0 degrees to 6 degrees, which of the following things will happen? The water will. Okay, so let me just have some time to talk about this, right? This is really fascinating. In fact, this is an extensive application to life in the aquatic world, and we talk about evolution and continuity of aquatic life. This is just the physics of that. And so this is what happens to water. When you're cooling water from a higher temperature, right? Let's say from 25 degrees Celsius room temperature, and then we cool it to 10 degrees Celsius, nothing is happening. The water is just cooling, and it's in that process it's actually shrinking, right? So you get it down to 5 degrees Celsius, it shrinks. You get it down to 4 degrees Celsius. The moment you get to 4 degrees Celsius, what begins to happen to the water is it begins to expand. And so when you get closer and closer to 0 degrees Celsius, where the water has to freeze, you realize that the water is continuously expanding, such that when it eventually freezes, the same mass of water now has a bigger volume, and so the density has reduced. And so that's why ice floats on water, right? And so you realize that, boom, ice floats on water, and so the surface layer of water is so cold that it basically insulates, because ice is a really terrible conductor of heat. It therefore insulates the underneath portion of the water, and so the liquid water underneath it basically almost maintains the same temperature for aquatic life to survive. This is so cool. This is a very good question. I love it. And so the answer is basically like we've explained. So if water is warmed, okay, from 0 degrees to 6 degrees Celsius, so it first of all contracts, right? It contracts first. All right, so clearly good. So this is the answer: contracts first, then expands. So it contracts till it gets to 4 degrees Celsius, and you continue to heat it, then boom, it begins to expand. All right, perfect. Okay, so this question is actually a question on capacitors. So what we're going to do, we're just going to quickly do the necessary calculations here before we even read the options. So the first thing is these two capacitors are in series, so we're going to need to find the net capacitance. If they're in series, they behave like resistors in parallel. So the total capacitance is basically product of a sum, and so we get 2 microfarads. Now the next thing we're going to do is calculate the energy stored by this network of capacitors, which is basically half CV squared. So V now is actually going to be, or C now is actually going to be the net capacitance in this circuit, which is 2 microfarads. So we're going to calculate that net energy as this, and so that's going to give us 3.6 times 10 to the negative 5 joules. The next thing we're going to do is get the PD across each one of these capacitors. Now, but because there are just 2 of them in series, it means that this PD is shared between them, right? So if 2 volts, well, more PD will be dropped across this guy with a smaller capacitance. That's just how it works, because PD and capacitance have an inverse relationship. All right, so the more PD will be dropped across the guy with a smaller capacitance than the guy with a bigger capacitance. And so because this guy is actually half, the capacitance of this guy is half these guys, the PD drop across this man will be twice the PD drop across the 6 microfarad capacitor. So the answer is just D. You don't even have to calculate it. The answer is actually D. But if you have to calculate it, the PD across the 3 microfarad capacitor will basically be 6 instead, all right, divided by 6 plus 3 multiplied by V. So they obey the potential divider rule just like resistors, but well, for capacitors you have to take this guy first, right? Divided by this guy plus this guy multiplied by the PD. Perfect. And so that's it down here, and so you get that, and so our answer is D, right? Because the PD across this 3 microfarad capacitor is twice the PD across the 6 microfarad capacitor. Okay, so this question is about temperature coefficient of resistance. So I'm just going to write out mathematically the expression that governs that. So the resistance of the conductor at a particular temperature theta is expressed like that in terms of our temperature coefficient of resistance or resistivity. Okay, so we are going to get r theta minus r0 divided by theta theta multiplied by r0 to be equals to our alpha. And so you realize that r theta minus r0 divided by theta theta is actually our slope. All right, so this is a slope. And so you realize that our alpha now is actually going to be the slope s divided by p. Okay, notice that p equals to r0, right? Because all of this thing like that is a slope, and so if we're dividing that by r0, then we can just replace that r0 by p, right? So that's our alpha, and so our answer is B. What is the electric field strength midway between the two particles, each carrying a charge of 2 microcoulombs, separated by a distance of that in air? All right, so this is not a problem. So we have two charges like this, so the distance between them is this. So midway, notice that these two charges are positive. So electric field is a vector. If I put a positive charge here, this guy is going to be repelling it, this guy is also going to be repelling it. So the electric fields at this particular point are opposite, but clearly the electric field at midway between the two charges, they are equal in magnitude and have the same charge. So the electric field strength midway here would basically be 0 because they'll cancel out midway. All right, now if you have to do that mathematically, then you are going to note that E midway is actually going to be E1 plus E2, of course vectors, k q1 over r squared minus k q2 over r squared, minus because, well, this guy is in the opposite direction. All right, so you notice that our k is of course 1 over 4 pi epsilon 0 because it's in air. So since q1 is equals to q2, you notice that our E is actually 0 Newton per coulomb. You did not have to do this mathematics. All right, so they have the same magnitude, then midway the electric field is 0. All right, so our answer is A. Okay, so we have a couple here. This question had a problem, right? It's a past question, I've seen it before. Well, you notice that we have this couple acting on this particular beam, right? So the distance between the two bodies, or it's basically these two forces, right? So basically the length of the beam, which is 0.8. So the torque here is basically the force multiplied by the distance, the perpendicular distance between the forces. Now, but notice that the way it's drawn, it shows that this force and the beam are perpendicular already. But this angle here, if this angle here was the angle between the beam and the force, then clearly the force and the beam are not perpendicular. So you would have to find the perpendicular component of this force about the beam, about the length of the beam. All right, and so in this case we'll just have to be multiplied by 0.8, right? Because I mean it's not well drawn. The problem has a problem really. So we have the answer to be 2.4 Newton meter, but there's no answer there. All right. But if this 60 degrees was the angle here, then you would have to resolve, and so you would take 3 sine 60, right? So 3 sine 60 degrees become the perpendicular component. Sine 60 is of course root 3 on 2, and so you're actually going to have multiplied that with 0.8, which gives us, I think, 6 root 3, right? So if this 60 degrees was actually up here, this would have been the answer. Okay, again, it's a problem, so there we go. Okay, so in this question we want to find the potential over at n, and so what we're basically going to do is, of course, the potential at n is sum of the potential at n due to y and the potential at n due to x. And so v at n is vy plus vx, and so we can actually represent that. Because v is not a vector quantity, we're just going to stick with the signs on the individual charges. And so that's why you notice a negative here. All right, because, well, the potential due to y is actually a negative potential at n. And so we are going to get of course magnitude of qx equals to qy, which is equals to q. And so you notice that our v at n is basically kq. We can factor out this kq, right? Because qx and qy are equal, over 1 over rxn minus 1 over ryn. And so our result is actually Vn to be negative 9,000 volts. But the answer here is only negative 90 volts, which is a problem, right? That was a mistake. And so we're going to have known as the answer. A ball rests upon a flat piece of paper on a tabletop. The paper is pulled horizontally but quickly towards the right as shown. Okay, so I'm going to explain this problem using written text. Okay, then we're just going to discuss it, and that's it. So I'm going to display it here. So according to Newton's first law, a particle at rest continues at rest unless acted upon by a resultant force, right? Of course, that's one component of the law. The full law states that a particle at rest or moving in a straight line with a uniform velocity continues to do so until acted upon by a resultant force, right? So we have so a particle at rest continues at rest unless acted upon by a resultant force. Pulling the paper exerts a force on the paper and not the coin. Therefore, relative to its original position, the coin is still at rest and not moved. I think a good way of exemplifying this is when you put a coin on top of a cardboard paper which is placed on top of a bottle. You sting the cardboard paper so quickly, the coin directly drops into the bottle, right? That tells you that, well, you've simply transferred momentum to the paper, and so the coin is still at rest. It has no momentum acting upon it because there's no force acting upon it, and so it basically drops into the bottom. So that's exactly the same thing that's happening here. But let's go ahead and explain with this, or look at what I've written here. So with friction, the coin moves slightly in the direction of the frictional force acting on it. That is Newton's second law, which basically states that the rate of change of the time rate of change of linear momentum is proportional to the net force acting on it and takes place in the direction of the net force. And so you realize that the net force acting on the coin in case where there's friction, or the ball in this case, would basically be to the left, right? And so it's going to have a momentum change in that direction, but originally the particle is at rest, and so it would basically have to move to the left to have a momentum change in that direction, right? Perfect. And you have, however, if the paper is pulled so quickly, the time the frictional force acts on the coin is very small, thereby imparting a small impulse on the coin, resulting in a change in its momentum in the direction of, it's very small change in its momentum. I needed to add that there, in the direction of the frictional force, right? Again, Ft equals to change in momentum. So if t is very small, you realize that the change in momentum will also be very, very small. And since initial momentum is basically zero, then we're basically talking about the final momentum, right? So the particle moves very gently to the left. Perfect. And so you have a scenario where you have statement 1 and 2 being correct. Statement 1 says remain stationary if there's no friction between the paper. Statement 2 says move to the left if there's friction between the paper and the ball. Perfect. And so our answer is A. Comparing the conduction of electricity along a uniform wire with the conduction of heat along a lacked metal bar, which of the following statements are correct? Okay, so I'm just going to do the mathematics here. So for thermal heat transfer, we basically have the Q dt, the rate at which heat is propagated along the metal bar, is basically Ka d theta on L. Now we can write out the expression for current, electric current. So you notice that according to Ohm's law, it's basically V over R, and we can notice that in place of R, since R is basically the resistivity of the material multiplied by the length divided by the cross-sectional area, we can replace that with that quantity. And so you notice that we now have our current to be VA over rho L. Now 1 over resistivity gives you conductivity. All right, so this is electrical conductivity. We're just going to call that tau, all right, because this K here is thermal conductivity. This guy is tau, standing for electrical conductivity. You have A, the cross-sectional area of the wire, you have V, the potential difference between the two ends, and then you have L, the length of the wire. So we can compare these two relationships now, the dq dt for charge, which is basically current, because current is the rate at which charges flow through that conductor. And so you actually have current here to be dq dt, which is tau AV over L. We can also get dq dt, which is now for heat transfer, to be Ka d theta on L. So you notice that electrical conductivity K, or thermal conductivity K, is analogous to electrical conductivity tau, and cross-sectional areas are analogous to cross-sectional area. V, the potential difference between the two ends of the wire, is actually analogous to the temperature difference across the ends of the metal bar. And of course we have the L there. So you notice that our answer is A. The diagram in figure 10 below shows the electric field lines in a region of space containing two small charged spheres, Y and Z. Then one Y is negative and Z is positive. Well, I've explained again using some statements here. Because the direction of the field lines indicates the direction of the force the charge exerts on a unit positive charge placed at a point in the field, you have that y must be positive, repelling the unit positive charge, right? Because this y, you notice that the field lines are leaving, and these field lines, the direction of these field lines are indication of the direction of the force this charge exerts on the unit positive charge. So if I place a unit positive charge here, this guy is going to be pushing it away, all right? So it's going to be repelling the unit positive charge away. It means that this guy must itself be a positive charge, because like charges will repel. But this guy is attracting that unit positive charge. That's why the field lines are entering, and so this guy must be negative. And so this statement 1 is wrong, right? Z is rather negative and Y is positive. Statement 2 says the magnitude of the electric field is the same everywhere. Well, that's not true. If these guys are oppositely charged, because you see this guy is negative, this guy is positive, it tells you that all along this line joining their centers, the electric field is enhanced. Okay, electric field is enhanced here. So if I put a positive charge, this guy is pushing away, this guy is attracting the positive charge. It means that the electric field here is basically the sum of these two electric fields. All right, now but if I come all the way from the line joining their centers, all right, so if I get over here or over here, you notice that the electric field here would not be enhanced, they'll be opposing each other, and so the electric field due to Z and the electric field due to Y can get to a point where they basically cancel out, and you have zero electric effect. And so at that point you talk about as a point of null electric field intensity. Okay, and yeah, so it clearly tells you that it's not possible. This is not true. The magnitude of the electric field is the same everywhere. It's not true. It's only true for actually regions where you actually have a uniform electric field. For instance, the region between the plates of a capacitor, that's where you have a uniform electric field. 3 says the electric field is not zero anywhere except infinitely far from the spheres. Okay, this is going to be true only if these two spheres, Y and Z, have the same magnitude of charge. All right, so maybe the charge on Z is pure, the charge on Z is negative, Y is negative, or this guy is pure and then this guy is negative pure. So only in that case where they have the same magnitude of charges that you're actually going to have the resultant being at infinity. All right, any other case that will not be true. All right, so the only statement here that can be true is statement 3. So the answer most likely is D. Thank you guys so much for watching the video till the end. I hope you enjoyed it. If you want to enjoy more physics content like this, please consider subscribing, turning on that notification bell. We're going to bring in a lot of work, a lot of tutorials. We hope you stick around to enjoy every one of them. Thank you so much.